Separation of mixtures of CO2 and C2H6 is relevant in the context of natural gas processing. Current technologies for CO2 C2H6 separations use extractive distillation because of azeotrope formation. In my presentation today, I'm going to discuss a different strategy for separating mixtures of CO2 from C2H6, and this strategy relies on anti-synergy between mixture adsorption and diffusion in microporous crystalline materials. In particular, I'd like to consider separations using DDR zeolite that consists of cages separated by narrow windows with an aperture size 3.65 angstrom. The shortest aperture distance and the longest distance is 4.37 angstrom. Both of these gas molecules jump lengthwise across the windows, and since the cross-sectional dimension of CO2 is smaller than that of C2H6, the mobility or diffusivity of CO2 is significantly higher than that of C2H6. Let's look at experimental data on transient uptake within crystals of DDR zeolite. The experimental data are shown by the symbols. The red circles are for CO2 and the blue squares are for the uptake of C2H6. At equilibrium, the loading of C2H6 is significantly larger than that of CO2. However, if you look at the initial transients, we note that the CO2 loading within the DDR crystals is significantly higher. This is because of the higher mobility of CO2. The pores are initially filled with CO2 before they reduce in the loading to reach the equilibrium value. So there is an overshoot in the CO2 loading during the initial transients. To model these experiments, we resort to the Maxwell-Stefan diffusion equations, and the expression to describe the transient uptake of the component loadings is described by this partial differential equation, where Qi is the molar loading of component I at any position R within the crystallite, which is assumed to be spherical, at any time t. This time derivative is related to the molar flux of species I, and the molar fluxes are described by the Maxwell-Stefan diffusion equations as being proportional to the gradient of the chemical potential of species I, and the proportionality constant is the Maxwell-Stefan diffusivity d sub I. Rho is the framework density of DDR. The experimental data can be matched taking the ratio D1 divided by D2, the ratio of the Maxwell-Stefan diffusivity of CO2 to the C2H6 to be 1333. And there is another parameter that is important, and that is the ratio of the Maxwell-Stefan diffusivity for component 1, which is CO2, divided by the square of the radius of the crystallite. And to match the experiments, we take the diffusional time constant to be 0.125 per second. I'll return to these parameters later in my presentation. So the mixture adsorption equilibrium favors C2H6, but the diffusion selectivity favors CO2, and we would like to cash in on the anti-synergy between adsorption and diffusion to achieve the separation of CO2 C2H6 mixtures in fixed bed adsorbers. For a feed mixture, say 50-50 CO2 C2H6, we would like to recover purified C2H6 in the adsorption phase. In other words, we would like the pores to selectively take up the more mobile component. So we need to achieve or realize kinetic separations. Let's summarize the adsorption and diffusion characteristics of mixtures of CO2 and C2H6 in DDR zeolite. We define the adsorption selectivity as the ratio of the component loadings of CO2 to C2H6 divided by the corresponding ratios of the partial pressures. The adsorption selectivity favors component 2, which is ethane. We define the diffusion selectivity as the square root of the ratio of the Maxwell-Stefan diffusivity of component 1 to that of component 2, that is CO2 to C2H6, and the diffusion selectivity favors CO2. So we have a scenario in which the adsorption selectivity is smaller than unity and the diffusion selectivity is larger than unity. In other words, we have anti-synergy between adsorption and diffusion. There is another parameter that is relevant to describe separations in fixed bed adsorbers, and that is the ratio of the Maxwell-Stefan diffusivity to the square of the crystallite radius. This is often called the diffusional time constant. This parameter quantifies the severity of diffusional influences. If this value is very large, there are no diffusional influences and it is impossible to achieve kinetic separations. So in order for kinetic separations to be realized, we need to have a high degree of diffusional influences, and this is achieved by choosing crystallite sizes that are relatively large. Watch also my presentation on synergistic mixture separations with MOFs and transient breakthrough simulations on my YouTube channel. Let us now move on to separations in fixed bed adsorbers and see how we can exploit the anti-synergy between adsorption and diffusion. I present here transient breakthrough simulations for separation of 50-50 mixtures of carbon dioxide and ethane operating at a temperature of 298 Kelvin at a total pressure of 20 kilopascals. These 4 simulations are for increasing sizes of the crystallites, increasing from A to B to C to D. With increasing crystallite size, the diffusional time constants defined as the ratio of the Maxwell-Stefan diffusivity for component 1, that is carbon dioxide, to the square of the crystallite radius is here 0.5 per second, is Here in case B, 5 times 10 minus 3, 1.25 times 10 minus 3, 2 times 10 minus 4. So with increasing particle size, we have a decreasing trend in the diffusional time constants. The ratio of the Maxwell-Stefan diffusivities of component 1, CO2, to component 2, that is ethane, is held constant at 1,333, corresponding to the value obtained from the experimental data for transient mixture uptakes discussed in the first slide of this presentation. Now let's consider this scenario A, in which the diffusional time constant is 0.5 per second. We note that CO2 breaks through earlier than ethane, and therefore purified ethane cannot be recovered in the adsorption cycle. The diffusional influences are not strong enough to result in selectivity reversals. In the scenarios considered in B, C, and D, the diffusional time constants are progressively lower, and that results in the breakthroughs of ethane at earlier times than the breakthrough of CO2, and therefore purified ethane can be recovered in the adsorption cycle. With decreasing diffusional time constants, the breakthrough of ethane occurs earlier. But if the diffusional time constant is very low, both the breakthroughs occur earlier, and therefore the distance of separations are significantly influenced by the choice of the particle size and therefore the diffusion time constant. Let's see whether there is an optimum value for the diffusional time constant. For 4 different values of the diffusional time constants corresponding to 4 different choices of the crystallite size, I plot in this graph the percentage of ethane leaving the fixed bed adsorber as a function of a modified time parameter defined as the flow rate Q0 at the inlet to the fixed bed times the actual time divided by the mass of adsorbent. The units of the x-axis liters per kilogram. Let's assume that the desired purity of the product ethane that is to be recovered in the adsorption cycle needs to be larger than 90%. From a material balance, we can determine the productivity of 90% plus pure ethane and plot this as a function of the diffusional time constant. With increasing particle size, the diffusional time constant would decrease and the productivity of purified ethane would increase. However, if the particle size is too large, then the productivity of ethane is reduced. So there is an optimum particle size or optimum diffusional time constant that results in the maximum purity of the desired product in the adsorption cycle. I refer you to my paper published in 2023 in Precision Chemistry for further details of the influence of diffusional time constants on productivities in kinetic separations. For a chosen crystallite size, the mixture separations are strongly influenced by contact time between the gas mixture and the crystallites. For separations of CO2, C2H6 mixtures with DDR zeolite, I consider here a set of 4 simulations in which the particle size is held constant and the chosen particle size yields a diffusional time constant of 1.25 times 10⁻³ per second. The ratio of the diffusivity of CO2 to C2H6 is 1333. The length of the fixed bed adsorber is fixed at 0.3 meters, but the entering gas velocity is varied to yield 4 different contact times between the crystallite and the surrounding gas mixture. Let's define V as the interstitial velocity, which is defined as the superficial gas velocity divided by the porosity of the bed. And in scenario A, I have L, which is the length of the fixed bed divided by the interstitial gas velocity, equals 600 seconds, which is the contact time, average contact time. In this case, the contact time is 300 seconds. This is 30 seconds, and it's 3 seconds. So with increasing superficial gas velocities and increasing interstitial gas velocities, we have decreasing contact times. Let's look at the scenario in which the contact time is 600 seconds. The time is so large that the bed operates close to equilibrium, and the first component to elute the fixed bed is CO2, and there is no selectivity reversals. In order for selectivity reversals to occur, the contact time should be shorter, and we see indeed that with a contact time of 300 seconds, ethane elutes the fixed bed earlier, and with decreasing contact times, the ethane elutes progressively earlier, and at 3 seconds contact time, the elution of ethane occurs at a value of say 0.5 for the x-axis, which is the modified time parameter expressed in liters per kilogram. Let us see how contact time influences the productivity of purified ethane. In this graph, I plot the percentage of ethane in the gas mixture exiting the fixed bed for 3 different scenarios in which the diffusional time constant is held constant at a value of 1.25 10⁻³ and we have 3 different values for the contact time between the gas mixture and the crystallites of DDR zeolite. The red curve is for contact time of 300 seconds. The blue curve is for a contact time of 30 seconds. And the black curve is for a contact time of 3 seconds. On the basis of a material balance, we can determine the productivity of purified ethane containing less than 10% CO2 using a material balance on the fixed bed adsorber. The productivity of purified ethane of the required purity is plotted as a function of the contact time between the gas mixture and the crystallites. We see that the productivity increases when the contact time is lowered. A lowering of the contact time implies stronger diffusional limitations because the crystallites have not been exposed to the gas mixture for sufficiently long times in order for equilibrium conditions to prevail. So long contact times implies closer approach to equilibrium and less effective kinetic separations. So kinetic separations are more effective with larger crystallite sizes and shorter contact times.